In exercise 2.5, we have to find the microstates for different Einstein solids. The first one, case A, has n equals to 3 and q equals to 4. So now we can use the general formula to find the number of microstates in an Einstein solid with n oscillators and q units of energy, which is equals to q plus n minus 1 factorial over q factorial times n minus 1 factorial. So now we can substitute our values and we get that the number of microstates for 3 and 4 is equals to 4 plus 3 minus 1 factorial divided by 4 factorial times 3 minus 2, which is just 2 factorial. So plugging my calculator, we get 6 factorial divided by 4 factorial times 2, 2 factorial is 2, and is equals to 15. Then for case B, we have n equals to 3, q equals to 5. So we have to use the same formula again. So this one right here, just going to write 5 instead of 4. Oops. Okay. So we're going to have the top 7 factorial divided by 5 factorial times 2, which is equals to 21. For C, again, we're going to have n equals to 3, q equals to 6. So same thing again, take it, let's change our 5, which now became 6. So we're going to have at the top 8 factorial divided by 6 factorial times 2, which is equals to 28. Write better, 28. Then we have D with n is equals to 4, q is equals to 2. And our formula right here is going to be equals to, we'll change this. I should just read it. Alright, so 4 and 2. So we're going to have 2 plus 4 over 2 times, and then we're going to have 4 minus 1, so just 3. So the top we're going to have 5 factorial divided by 2 factorial, just 2, times 3 factorial, which is equals to 10. Then we have E, where we have n is equals to 4, q is equals to 3. So same thing, pretty much. Here we're gonna have, oh no, that was correct. 3, 3, 3, okay. That means that on the top we're gonna get 7 factorial, no, 6 factorial, what is better? 6 factorial divided by 3 factorial, so 3 factorial, which is equals to 20. Let's check our solutions for the moment, and this should be correct. This is exercise 2.5. Okay, so we have 15 for the first one, 21 for the second, 20 for the third, 10 for the fourth, and 20 for the fifth. Now we're going to get into the ones a little more complicated. We're going to have f is equals to, well, for f, we have n equals to 1, q equals to anything, so I'm just going to call it q. I don't really care about it. So our multiplicity is going to be equals to 1, comma q, substituting q plus 1 minus 1, divided by, going to have q factorial times, well, we're going to have 1 minus 1, so 0 factorial, which is just 1. Anyhow, here we cancel these two. We're going to get q factorial on top divided by q factorial on top, which is simply equals to 1. It's the same thing. Then g, we have n equals to anything, so just going to n again. Q is equals to 1. So same thing, n comma 1. So we're going to have 1 plus n minus 1 factorial. I forgot over here. Okay. Over n, sorry, 1 factorial, which is going to be 1, n minus 1 factorial. So here we can cancel these two. We're going to get n factorial divided by n minus 1 factorial. And if you remember, n factorial just means n times n minus 1 factorial. So we can substitute it in. We're going to add times n minus 1 factorial divided by n minus 1 factorial. So cancel these two out, we obtain n. Now I want to go back to this one, just in case you don't really get it. So we're going to have it simply equals to n times n minus 1 times n minus 2 times n minus 3. But at the same time, n minus 1 factorial is equals to n minus 1 times n minus 2 times, of course, so on, times n minus 3, so on. So this part here is just simply going to be this part right here. You see the connection. Okay. And that's the end of exercise 2.5.